Welcome to This Explainer. Today, we're diving straight into the invisible, highly electric world all around us. We're going to uncover the unseen forces that govern literally everything, from the everyday friction of the clothes you're wearing right now to those massive, powerful storms lighting up the night sky.
So let's kick things off with a real-world scenario I know we've all experienced. Okay, picture this. You're sliding across your car seat, you reach out to grab the metal door handle, and zap. You get that sudden, sharp, and let's be honest, incredibly annoying little shock. But what is actually happening right there to cause that?
Well, the answer is a sudden discharge of accumulated electric charges right through your body. As you slide across an insulating surface, like that fabric car seat, invisible charges are actually building up on you. Then touching that metal door rapidly discharges them all at once. It's the exact same science behind the spark or that crackle you hear when you pull off a synthetic sweater in dry weather. This is electrostatics in action. It's the behavior of static electricity, which basically means charges that aren't actively moving, until they suddenly do.
And honestly, this brilliantly illustrates how the whole concept scales up. Because the lightning illuminating a severe thunderstorm, that is just a massive atmospheric electric discharge. The exact same fundamental physics causing that tiny zap from your car door is totally responsible for a lightning bolt. And get this. That discharge is so powerful, it can heat the surrounding air to 5 times the temperature of the sun's surface. Crazy, right?
So, to see where all of this began, let's jump into Section 1, Uncovering the Electric Charge.
Way back around 600 BC, the Greek philosopher Thales of Miletus made this really fascinating discovery. He noticed that if he rubbed amber with wool or silk, it suddenly started attracting light objects like pieces of straw or bits of paper. It was such a profound observation at the time that the very word electricity is actually derived directly from electron, which is the ancient Greek word for amber. Over centuries of experiments since then, scientists realized there were 2 distinct kinds of electrification. If you rub a glass rod with silk, it acquires one kind of charge. But rub a plastic rod with cat's fur and it acquires another. It was the American scientist Benjamin Franklin who conventionally named these positive and negative. And together, they established a really simple yet absolutely profound rule. Like charges repel each other, while unlike charges attract.
But how exactly does this happen on a microscopic level? Let's take a look at Section 2, How Objects Become Electrified.
Normally, matter contains perfectly balanced charges, which makes objects electrically neutral. But when 2 neutral objects rub together, friction totally changes the game. In solids, some electrons are just less tightly bound to their atoms. So the physical act of rubbing literally strips those loosely bound electrons from one material and forces them onto the other. The object that loses the electrons becomes positively charged, and the one gaining them? That one becomes negatively charged.
Now, the absolutely crucial takeaway here is summarized perfectly by this quote from our source material. No new charge is created in the process of rubbing. We aren't magically generating electricity out of thin air here. We're simply shuffling a tiny fraction of pre-existing electrons from one surface over to another.
Now, if everything in the world is made of atoms, why do only certain materials give you those static shocks? Well, that brings us to Section 3, Insulators versus Conductors.
The fundamental difference here really just comes down to mobility. When an electric charge is transferred to a conductor, like, say, a piece of metal, or even the human body, it readily distributes itself over the entire surface. The charges can move around freely. In stark contrast, if you place a charge on an insulator, think nylon, plastic, or glass, it stubbornly stays exactly where you put it. And this actually answers a great everyday question. Why doesn't a metal spoon give you a static shock when you rub it? Well, it's because both the metal spoon and your body are conductors. Any charge you try to build up by rubbing it simply flows seamlessly through the spoon, right through your body, and directly into the ground. It literally never gets the chance to accumulate and give you that sudden zap.
All right, now that we understand the basics of electrification, let's move to Section 4, the rules of charge. Meet Charles Augustin de Coulomb. Now, he wanted to do a lot more than just observe. He wanted to quantify exactly how much force these invisible charges exerted on one another. So using a remarkably delicate instrument called a torsion balance, he actually managed to measure the precise forces between charged metallic spheres.
And his groundbreaking findings became known as Coulomb's law. He discovered that the electrical force between 2-point charges is inversely proportional to the square of the distance between them.
To put that in plain terms, if you move the charges further apart, the invisible force between them drops off dramatically. But he also found the force is directly proportional to the product of the charges, meaning if you make the charges bigger or bring them closer together, that invisible force spikes exponentially.
Beyond Coulomb's law, we have another golden rule to look at: the quantization of charge. You see, electric charge isn't some continuous smooth fluid that you can just pour out in any random fraction. Instead, as the formula indicates, all free charges are integral multiples of a basic indivisible unit. Think of it like rungs on a ladder. Charge comes in very specific, microscopic packets. It's exactly the charge carried by a single electron or proton. You simply can't have, say, half an electron's worth of charge. It just doesn't work that way.
And our final golden rule is the conservation of charge. In our vast universe, the total charge of an isolated system remains completely unchanged over time. You cannot create or destroy net electric charge. You can only shuffle it around. Even when nature spontaneously creates charged particles, like a neutron suddenly turning into a proton and an electron, the equal positive and negative charges perfectly cancel each other out. The universe's grand ledger of electric charge is always perfectly balanced.
So we've seen how the simple friction of a sweater mirrors the explosive, terrifying power of a lightning strike, and it's all governed by strict universal mathematics. The forces holding every single atom and molecule in solids together, the sticky pull of adhesive tape, and even the surface tension of water, they are all fundamentally electrical in nature. So I'm going to leave you with this thought. If these electrical forces dictate the very structure of our material world, what else might we achieve by fully mastering them? Thank you so much for checking out this explainer, and keep learning.